First of all, thank you very much for the invitation and for the opportunity to talk. Thank you for being here after lunch. It's always hard. So today I want to talk about about the Novikov conjecture on stratified spaces. So this is a conference on interactions of non-commutative geometry with mathematics in general, and this is maybe one of the great successes of non-commutative geometry, the solution of the Novikov conjecture, depending on the group. But for those groups for which it has been established, it was certainly one of the great successes. So let me remind you what the Novikov conjecture says. So we have an orientable closed compact manifold. Gamma is the fundamental group, and we have a Galois gamma covering. So this can be the universal cover, for example. And so we know that there is a classifying map from X to B gamma. And we also know that from the Hirzebruch L-class in cohomology, by Poincaré duality, we can construct the homology L-class. So this is a homology class, just the Poincaré dual of the Hirzebruch L-class. And the Novikov conjecture, this is one way of stating it, says that if you pair the push forward of the L-class in the homology of B gamma, if you pair it with classes in the cohomology of B gamma, so these are numbers, these are oriented homotopy invariants. Okay? This is the Novikov conjecture. It is still open in this generality. There have been many ways to attack this conjecture, and one of the best is to pass through the strong Novikov conjecture. So what does the strong Novikov conjecture says? Well, the strong Novikov conjecture for a group gamma is very simply this statement, namely the assembly map, the natural map from the K-homology of this topological space to the K-theory of the reduced sister algebra is rational injective. Okay? So if gamma is torsion-free, this is the Baum-Cohn map, otherwise it is not, but this is the map we want to look at. And it is a theorem, an important theorem, that says that if the strong Novikov conjecture is true, then the Novikov conjecture is true for a space with that fundamental group, with gamma equal to that fundamental group. So this is a consequence of really 5 facts that I want to remind you or tell you about. So first of all, the first fact is that there is a K-homology class attached to the signature operator on this manifold. The manifold is oriented, and therefore there is a signature operator, which I denote in this way. So it's a generalized Dirac operator. This is why I use this notation. Second, there is an index class called the Mishenko index class, or it has many names. But what you do is you consider this bundle of finitely generated projective modules over the sister algebra. So this is basically X prime. So this is the covering, okay? And so this is the covering. This is gamma acting on the covering by deck transformations, gamma acting in a natural way on the sister algebra. You consider this bundle. And you can twist your signature operator by this bundle. Okay? You have to make sense of this, but there is a well-established theory due to Mishenko and Fomenko. And so you get a K-theory class. Okay? You can think to the kernel and co-kernel of this operator as finitely generated projective modules, and they give you, over the sister algebra, they give you this class. I mean, this is not strictly speaking true. You have to perturb, but let's not get into the details. Okay. The third point, very important point, is that this index class is a homotopy invariant. Okay. There are a number of proofs of this basic fact. There is a proof that shows that this index class equals the Mischenko symmetric signature, which is an a priori invariant, homotopy invariant. But you can give a purely analytical proof of this fact, which is due to Hilbert and Skandalis. Okay, this is a very important point. And well, another point is that you have this cohomology class. You can take the chain character, and you land in the homology of X, and you have this equality. Okay, this equality is more or less the Atiyah-Singer index theorem. Okay. And so, by functoriality, you also have this equality. Okay. If you push forward the fundamental class, the signature class, through the classifying map, and you take the chain character, you get precisely the push forward of the L-homology class. And the last piece of information that you need is that if you take the assembly map and you apply it to this class, you get precisely the index class of Mischenko. Okay. Now, it's a really easy exercise to deduce the Novikov conjecture from these facts. Okay. Simply because what you want to show, your goal is to show that this homology class, the push forward of the L class, of the L homology class, is an homotopy invariant. And if you, it's just an easy exercise to put together these 5 facts and prove it. Okay. So this is the way I think Mischenko and Kasparov, I don't know exactly, attacked and there have been many successes. You have translated completely the problem from a problem in topology to a problem in K-theory. Okay, this is how the interaction works. And let me point out that fundamental here is the fact that you have a good elliptic theory. I mean, this fact is elliptic theory, this fact is elliptic theory. This also can be framed as elliptic theory. I mean, there is a lot of elliptic theory going on. Okay. Now, my interest in this talk will be for stratified manifold, pseudomanifolds. So this is a space, a topological space that looks near a singular set, that in this case would be this one, as a bundle of cones. Okay, so I'll get back to this picture later. But so near there is a set, a singular stratum, around which your space looks like this. So this is the green circle is just a smooth manifold called the link of this point in the singular set, and the rest is all smooth. Okay. So this is a depth 1 example. There is only one singular stratum, but of course you can also look at more complicated examples where you also have other cones sticking out of this cone. So this would be a depth 2 example. Okay. So in this talk, I've given this talk 2 or 3 times, and I've seen that I cannot go beyond depth 1. People just don't follow. Okay, so I'll stick to this example. Okay, this example here. Okay. So, so what are the questions that we want to look at? Well, is there a homology class? So let me remind you, X hat is this singular manifold. Okay. Can we state a Novikov conjecture for this space? Is it true that the strong Novikov conjecture implies the Novikov conjecture? Because if it is true, then we have a set of examples which is very large at this point. Okay. So this is what I want to talk about. And so let me give some topological background for this problem. So first of all, let me remind you that on a singular pseudomanifold, on a stratified space, Poincare duality does not hold. And this led Goreski and McPherson to define a new cohomology, which is called intersection cohomology. So this intersection cohomology depends on a function which is called the perversity, that tells you how your chains in the homology theory must intersect the singular stratum. So it gives you some bound on that. So you don't have a Poincare duality, but you have a generalized Poincare duality in the sense that you have a pairing between the intersection cohomology with perversity P and the intersection cohomology with the complementary perversity. Okay, so let me explain this. So this is what a perversity is, just a function from integers which are greater or equal to 2 to integers, satisfying this inequality. So the lower middle perversity is very important, is this. The upper middle perversity is this, okay? And the complementary perversity of a perversity is just defined by this equation. Okay. So unfortunately, as you can see, we don't have the same vector space. I mean, we have two vector spaces which are paired, but it's not the same vector space. Okay. And let me point out, since we will be working with that, that the lower and upper middle perversity are complementary. So the best you can say on a general pseudomanifold, stratified pseudomanifold, is that you have this pairing. Okay? And this pairing, unfortunately, is not enough because you want the same vector space in order to define signature. Okay? So finally, another piece of information is that intersection cohomology is a stratified homotopy invariant theory. It's not a homotopy invariant theory. Okay? It's a stratified homotopy invariant. Okay? So this is topological background. Other questions? Okay. Now, another piece of background I want to give is a very nice description of the homological class, which is due to Tom. So his point of view for the homological class was the following. Take a sphere of dimension k with k satisfying this inequality, n is the dimension of your manifold. And you take the cohomotopy groups of X. So these are just maps, homotopy classes of maps from X to this sphere. And to cohomotopy, you can associate a map that sends a cohomotopy class to the signature of the anti-image of the North Pole. Okay. So this goes into Z. Okay. Of course, you have to take F transverse to the North Pole in such a way that this is, I mean, you have to do something to show that this is well defined, okay? But this way, now, you know that in this range, there is an isomorphism between rational cohomology and rational cohomotopy. And so this map gives you an element here, okay? The homomorphism from the cohomology to the rationals. And this is homology. So this defines, Tom shows that this defines the K part of the homology class. And if you don't have that inequality, you simply cross with spheres and use the Q-net theorem and you reduce to this case. Okay? So this is a way to describe the homology class, and the bottom line is that in order to define the homology class, you must know how to take the signature of certain submanifolds of X. That's, you know, the outcome of this discussion. Now, let me consider a special case. I will not talk about this today, but I want to recall. So, a Witt space is a space for which the link has this property. Okay, so let me go back one moment to that picture. So I want to invest a little bit of time on that picture. So remember, what is that picture? So we have the singular stratum, which actually was in blue in my picture. This is not blue. This is green, but anyway. So this is Y. And then you have this cone bundle. You have this cone bundle. And so this is an element P in the singular stratum, and this is the link of P, LP. This is the link of P. In this picture, this is the depth 1 picture, this is just a smooth manifold. So, okay, but in general, it will be another pseudomanifold of depth 1 smaller. Okay. Now, this space is Witt if no. Which one? This one? Oh, okay. Oh, thanks. Yeah. So if this happens, okay, so this is the condition. So in our case here, we are simply saying that this closed manifold is either odd dimensional, or if it is even dimensional, it does not have any cohomology in middle degree. You see, middle degree is the dimension of the link divided by 2. This is what a Witt space is. Okay, so in this case, this L is either odd dimensional, or if it is even dimensional, it does not have any cohomology in middle degree. Okay, only middle degree. This is what a Witt space is. I'll give examples in a moment. Now, the magic is that if X is Witt, this is a theorem due to Siegel, I think, then these two cohomology are the same. And so now you are in business because you have Poincare duality. Okay? You really have a perfect pairing on this vector space. And so that means that whenever you have a Witt space, you have a well-defined signature. And now you can show that, you know, the anti-image of the North Pole is a Witt space as well. And so you have an homological class. Okay? That's very important. And so now you have your Novikov conjecture. Okay? You can define the higher signatures. And the theorem, so this is a theorem we proved probably in 2010 or 2011, was published in 2012, says that if the strong Novikov conjecture holds for gamma, where gamma is the fundamental group of X hat, then these higher signatures are stratified homotopy invariants. Okay? This is the theorem. As you can imagine, this involves a lot of analysis because you have to establish enough elliptic theory for the machine to work. Okay? And today I will talk about this, but in a more general case. Okay. Now, complex projective varieties are examples of Witt spaces. Other examples are certain quotients by non-free actions of Lie groups. For example, a semi-free S1 action produce a space like this where L is a complex projective space, and so if n is odd, you get a Witt space. But if n is even, you do not get a Witt space. Okay. So all this is in this published paper in Annales Scientifiques comme développement supérieur. Now, today I want to talk about something else. Namely, I want to talk about a more general set of examples. Okay? And so these we call Cheeger spaces. So Cheeger spaces are more general than Witt spaces, but they certainly not exhaust all stratified spaces. Okay. So here there are three papers we wrote. One is purely analytical. Another one is what basically I'm talking about today, but it rests a lot on this paper. And then here we connect with the topological theory that was done by Marcus Banagl. Okay. Now, first of all, since I will be using analysis, I have to tell you what kind of matrix I put on this on the regular part of this manifold. So let's get back to this example. Of course, doing analysis on this example means doing analysis on the regular part, namely you take out this singular locus. Okay. So the metric, so this I'm telling you who are the strata of these stratified spaces. So Y is this circle, is the singular set, and X, the regular part, is the other stratum, is the union of all these cones as the point runs over the bottom circle. Okay. So the link of this point here on the singular stratum is this closed compact manifold, the green manifold Z. Yeah. So here I called it L, but from now on I will call it Z. Okay. Now the metric we put, so in a neighborhood of a point, this is what you have. You have a cone over Z times a ball in the Euclidean space. And in fact, as a matter of fact, in a neighborhood of all the singular stratum, you have a cone bundle. T is a neighborhood of your stratum, singular stratum. You have this cone bundle here. So an iterated conic metric is just a metric that looks like that. Okay. So you pull back the metric on Y via pi. This is a symmetric two-tensor. And then this is the metric on the fiber, on the link, sorry, on the link. And this is the squeezing parameter. X is the variable on the cone. And then you have this dx squared. So this is this models a bundle of metric cones over this singular set. So doing a conic analysis on X hat means doing analysis on the regular part endowed with this metric. Okay. So now we are on a Riemannian metric, but you should, of course, keep in mind that this is an incomplete metric. This is an incomplete metric. So what are the preliminary problems? Of course, we want to do some elliptic theory, so we want to use some Hilbert space techniques, L2 techniques. And in this case, you want closed operators, right? I mean, that's always the case. And so you need to close up your operators, take the closure. So as you know, differential operators are always closable, and you have two closures. You have the minimal closure, which is simply the closure of the graph, and given by the closure of the graph, and then you have the maximal closure, which is defined distributionally. Okay. Now, if X is Witt, then a miracle happens, namely the exterior differential minimal extension is equal to the maximal extension, and similarly, the signature operator is that you know is symmetric on the compactly supported forms of the regular part, is essentially self-adjoint. So you only have one extension, and this, you know, helps you enormously. However, in general, in the non-Witt case, there will be many extensions between the minimal and the maximal. And similarly, this operator is not essentially self-adjoint. Okay? It has many different self-adjoint extensions. You will see some of it today. So now let me talk one moment about resolution. So if you have a pseudomanifold, you can always resolve it to a manifold with corners. Okay, I will talk about it now on this example. So this goes back to Verona, and then Bresley, Hector Saraleggi, and also we kind of gave some more information about this procedure in this paper. So this manifold with corners has an additional structure, namely it has an iterated Fabration structure on the bundle. Okay, this is a notion due to Richard Merrows. So that means that the hypersurface are fibrations, and then there are compatibility relations on these boundary hypersurfaces. Okay. But I will not get into that because, again, I'll do only this example, and here I can tell you easily what this is. Okay. So in this case, I'll get back to that in a moment. Well, actually, I'll do that immediately. So this is x hat. And the resolution is simply the manifold that you obtain by shrinking, I mean, by removing a tubular neighborhood to this singular set. Okay. So this is x hat. Doesn't come very well, but you just have to think that this is a tubular neighborhood which is conic, and you simply shift the conic of, say, 1. Okay. So x tilde is a manifold with boundary, and the boundary is a fibration with base equal to the singular stratum. So let me do this here. This is a terrible picture. I'll do it again. Okay. So the boundary of x tilde, now it's is this vibration that you have to think as a tube. Okay, so this is this. Okay. So let me call this vibration H over Y. And this is a vibration with fiber Z, the link. Okay, so this ZP. And this is the cone over ZP. Okay? So this is the situation. Okay. Now, the fundamental lemma that we shall use is the following. I look really at the theorem operator first, namely D plus D star, and not on at the signature operator. So I look at the theorem operator. And so recall that a tubular neighborhood is a bundle of cones here. This is the tubular neighborhood. So this part of the board is a tubular neighborhood. Okay. Now I consider the resolved manifold. Okay. So this is a manifold with boundary, and this is the boundary. So the boundary is this H, Y, Z. Okay. Now recall that if Z is even dimensional and the cohomology middle degree is not 0, then we are not in the Witt case. Okay? And now, to this picture, I can consider the following bundle. So let me tell you who is this bundle. Maybe I'll switch on the light. So this is the bundle, vector bundle with the fiber at P. So this fiber is simply the Hodge cohomology in middle degree of the fiber. So let me call this phi of phi minus 1p. So this is the Hodge cohomology. So by that I mean simply the null space of the Laplacian on this form of this degree. Okay. So this is a bundle that you look at often. Okay. This is a flat bundle, flat vector bundle by the Hodge theorem, this is actually a bundle. Dimension is always the same, and it's flat. I mean, you can even write down the connection, which is flat. Okay. Now, this is the bundle I want to look at. Okay. Now, let me try to. Okay. So the fundamental lemma is the following: if you take an element in the maximal domain of the theorem operator, so that means that U is in L2, and if you apply this operator distributionally to U, you remain in L2. This is the maximal domain. Then it has this asymptotic expansion. Okay? So this alpha 1 of U is an element in this Sobolev space of forms with values in this flat bundle. So you see here this flat bundle appears. Okay? And beta is also an element here. And U is an element of higher order. Okay? So here, as I said in this board, this is the flat Hodge bundle over Y, and the typical fiber is simply the Hodge cohomology of the fiber. Okay? So this is the key lemma, because now we will use alpha and beta to put boundary condition on our operator, and this is what Cheeger did in the isolated case, and we did it in the non-isolated case. Okay? So the way you do it, well, you look at these alpha and beta as Cauchy data to which you want to impose these boundary conditions. And so what you do is you fix a subbundle of this flat bundle, and you require that is a flat subbundle. This will be important in cohomological issues. So you simply take a subbundle, and then you require that form, alpha and beta. Well, alpha you require to lie in that subbundle, and beta you require to lie in the orthogonal subbundle. That's your bundle. That's your new domain. So you have reduced the maximal domain by requiring this boundary condition. Alpha, remember that alpha was here. Alpha was just a general section of the Hodge bundle, twisted by the zero forms. But now you require it to be in W, and this other one in W, perp. So this we call a Hodge mesoperversity adapted to G. Okay, you will see why it's we call it a mesoperversity. And it could be the zero bundle, yeah. Then you get the minimal domain, and if you get the whole bundle, you get the maximal domain.
Don't it looks a bit like Dirichlet and Neumann boundary conditions? Or it just looks the same as the homotopy?
You can look at it that way, yeah. That's in fact how Cheeger phrased it, yeah. Now in general, and this is actually a big complication in our paper, you have to set up a kind of iterative procedure, but as I said, I'm not going to talk about that. So a mesoperversity is actually a series of bundles, one for each singular stratum, and each bundle is a subbundle of the Hodge bundle with the previous boundary conditions. So here there is an iterative procedure which is too long to explain. So let me stick always to the depth one case. Now the techniques we use can be summarized in this slide. So if you write the theorem operator near the singular stratum with respect to this metric, then it has this form. Okay? N is the number operator on the forms. This one is the theorem operator on the base. This one is the theorem operator on the fiber. And then there are additional curvature terms that I'm not talking about here because they're higher order. Okay. And the fundamental idea is that instead of looking at this operator, we look at x times this operator. Now, x times this operator makes sense on this manifold with fibered boundary, and more, it's an element in the edge calculus of Mazzeo. So there is, at least in this particular case, there is a pseudo-differential calculus. And so we use a lot these techniques, which go back to Melrose, in order to prove the key lemma and, more importantly, to prove what I'm going to tell you in the next slides, which is the hardcore of my talk. So what are these results? Well, first result is that if you take a mezzo-perversity, so this calligraphic W means I am in the general case and I have this series of bundles. Okay. If you look at this example, it would be just one, and so it would not be calligraphic. So this actually defines, those boundary conditions define a closed self-adjoint domain. That's important. What is really difficult to show is that this is Fredholm with discrete spectrum. Okay, this is where the hard work goes. Also, we can define the same type of domain for the exterior differential on forms, and similarly for the formal adjoint of D. And these are mutually adjoint. Moreover, as in the usual case, the domain for the theorem operator is the intersection of these two domains. By the way, this shows that this is self-adjoint. Okay. Not only that, but if you take D restricted to this domain, then you get a Hilbert complex. Okay. Hilbert complex, the sense of Bruning and Lesch. And so now you can take the theorem cohomology groups. And these theorem cohomology groups are finite dimensional because of this Fredholm condition, and they are metric independent. Okay. So once you have that, actually this almost comes for free once you have the theory of Hilbert complexes. And there is a Hodge decomposition theorem. Also this comes from general results. Okay, so I mean this is what we were shooting for, right? I mean we wanted a Fredholm operator. I mean that's first elliptic theory we wanted. Now there are other things that we can say. First of all, if we have a mezzo-perversity, then there is a dual mezzo-perversity which is defined in terms of the vertical Hodge star. And now what you can prove is that there is a non-degenerate pairing. Okay. So if you take W equal to 0, this would be the pairing between the minimal L2 cohomology and the maximal L2 cohomology. And that, for Cheeger results, is the pairing between lower middle perversity intersection cohomology and upper middle perversity intersection cohomology. So this is why we call it mezzo-perversity, because it's a little bit more, it's between the two. Okay. Now, if it happens that you can choose a self-dual mezzo-perversity, then we say that your space is a Cheeger space. Okay. Now, you have topological abstractions to the existence of a self-dual mezzo-perversity. For example, you need this link to have a zero signature. Okay, in this case, the usual signature as a closed compact manifold must be 0. Otherwise, you cannot have this. Okay. So not all stratified spaces are Cheeger spaces. But what is important is that if you have a Cheeger space, then here, instead of the dual mezzo-perversity, you can put the mezzo-perversity itself. And then you have a signature, because now you have the same vector space. So you have a signature which is what you wanted to define. Of course, a priori, it depends on your choice of mezzo-perversity. Okay, it still depends on that. And also, you have a domain. If you have a self-dual mezzo-perversity, you have a domain for the signature operator. And this will be Fredholm. And if you use Hodge theory, as I recalled in the previous slide, you have this result, namely that the signature is the index. Also, there is a well-defined cohomology class. And finally, you have the index class, always depending on W, the Mischenko index class. So let me summarize what we got on so far. On a Cheeger space, once you fix a self-dual mezzo-perversity, admitting that you have one, I mean admitting you have a Cheeger space, well, what did you do? Well, you defined a cohomology depending on that mezzo-perversity, on that boundary condition. Then you defined a signature, which also depends on W, a cohomology class, and an index class. Okay. So this is what we got so far. So this is all kind of non-trivial elliptic theory. I mean, there is a lot of microlocal analysis in all this. And the natural questions you want to answer are, well, what happens to this invariance if you have a stratified homotopy equivalence? Remember that we have the Novikov conjecture in our mind. Okay. And another point is, well, how does all this depend on the choice of this W? Of this? So W, remember, for us is just a subbundle of this bundle. So in the self-dual case, this vector bundle has a natural kind of symplectic structure, and to be self-dual means being Lagrangian, with respect to that. Okay. Okay, well, here something really miraculous happens, and let me explain this. Well, for the stratified maps, no, there is what you expect. So let me get a stratified map, okay, between these two stratified manifolds. So what does that mean? It means that F sends the singular stratum of X hat, we are in the depth one case, to the singular stratum of M hat, and so the regular stratum goes into the regular stratum. So in particular, you see, we can lift this map to the resolved manifold. Basically, this comes from the definition. And since this is a stratified map, this F tilde is restricted to the boundary, is a Fabration map. Okay, so in other words, you have this commutative diagram. So this is this situation on X hat. This is this situation on M hat. This is the restriction of F tilde to the boundary, and you have this commutative diagram. Okay. Now, in general, it's a well-known problem that pullback on differential forms is not L2 bounded. As a matter of fact, it's not even a closable operator. Okay. And so this was, a preliminary problem that Hilsum-Skandalis had to solve when they gave this analytic proof of the homotopy invariance of the index class. Okay. So what they did was to replace F star by another operator, which I'm not going to explain. Okay. So we call that the Hilsum-Skandalis replacement. It involves, the Tom form, and it's a little thing, but you have to deal with that here. And the proposition you have to show is that if you fix a mezzo-perversity on the right-hand side and you pull it back through the Hilsum-Skandalis replacement, fiber by fiber, then you get a mezzo-perversity on X hat, the pullback mezzo-perversity. And if you started with a self-dual one, then this will be self-dual. I mean, here the only real issue we had to face was to ensure that this bundle was flat. This is not obvious, but you can prove it. Okay. So you can pull back mezzo-perversity, you can pull back this subbundle that you fix here, and the result is the following. If this is a stratified homotopy equivalence, then you have this isomorphism. I mean, provided you change the mezzo-perversity by the pullback, you have this isomorphism. Okay. And similarly, the signature behaves like this. So this is true in general. If W is self-dual, then this is what you have. And more generally, this is what you have in general. Okay. So this looks very much like the Hilsum-Skandalis result. You see, I mean, the homotopy invariance of the index class, but unfortunately you have this mezzo perversity kicking around, and you have to deal with that. Okay. So it seems like we are still far from something topological, but this is not the case. And the point is that you have a very important property, which is Bordism invariance. Okay, so you can give a natural notion of Bordism invariance. So if you have, you know, a Cheeger space here, so this is X hat, where you fixed this W, and here you have, I don't know how I call them there, M. Here you have M prime. Oh, let me put it this way. So this is M hat prime with another choice of mezzo perversity, and you assume now that you have a Bordism. And this Bordism is not only a Bordism of spaces, of singular spaces, but it also carries this mezzo perversity around. Okay, so this is what a Bordism of Cheeger spaces is. You keep track of this mezzo perversity. Okay. Now, if you do that, then you discover that this is use some KK theory. You discover that the signature and the index class of Mischenko are Bordism invariant within this notion of Cheeger Bordism. And now the really miraculous thing is the following. It's not really due to us, it's due to Banagl. We had to adapt his proof to this context, is that if you have two mezzo perversity on the same manifold, then this space with this mezzo perversity is Cheeger bordant to the same space with the different mezzo perversity. I mean, this is by far non-trivial. Okay, it's just a trick, but you have to think about it. And so now you see the corollary is that miraculously, really miraculously, these are both independent of the choice of W. Okay, and so now that means that you have an L class. And if you adapt certain computations of Moscovici-Wu, you can prove that the Chen character of the K-homology class is equal to this L class. Okay. So in particular, rationally, you see that also the K-homology class is not, does not depend on W. Okay. So these use some nice ideas of Moscovici-Wu. They have a couple of papers on this idea of the Chen character and the straight Chen character in Alexander Spanier cohomology. This is something that relates to the talk of Markus Pflaum. Okay. So this is a paper. This is the paper he was mentioning. Finally, since you are using KK techniques all around, you also have this fundamental fact. And so now I can finally, end of the game, I can state the main result. So remember, we just showed that we have an L class on a Cheeger space. So we can formulate the Novikov conjecture, exactly as in the closed case. And we can ask, are these higher signatures stratified homotopy invariants? And the theorem is the following. Theorem that we put on the archive almost 1 year ago, is that if the strong Novikov conjecture holds for gamma, where gamma is the fundamental group of your Cheeger space, then this Novikov conjecture holds. Okay. And the proof is the same as before, because we have, you know, the 5 facts that I want to remind you. Namely, we have a K-homology fundamental class. We have the index class of Mischenko, as I said, independent of W. And this is a stratified homotopy invariant. You can show that. We showed it, basically. And also you have this from from Moscovici-Wu, therefore you have this point. And finally, you have the fifth ingredient, which is that assembly sends this class to the index class of Mischenko. Once you have these 5 facts, you had to sweat a lot to get them. The proof is exactly the same. So I think more or less my time is over, so I can thank you for your attention.